We have been talking about Maxwell's equations, and what we are going to do today is talk about how Maxwell's equations lead to existence of electromagnetic waves. What we mean by electromagnetic waves are these electrical and magnetic disturbances that sustain each other and propagate in space. To understand it fully, we should actually first understand what waves are. Waves and wave equation. So, in this lecture today, we are going to spend some time to understand what wave equation is, where it comes from, what wave phenomena is. I am going to talk about non-dispersive waves. By non-dispersive, I mean a wave that does not distort as it moves. Simply put, this is what it is. So, let us understand what a wave is. In particular, we want to understand, does a wave mean that a material, particle moves from one place to another? And the answer is no. For example, you have seen water waves, where if I make a disturbance, it travels out, but we do not see water going out. Similarly, when I am speaking, there is a pressure wave that is going, but it does not mean that air is moving from one side to the other with this pressure wave. What happens is, in a wave, there is a disturbance that travels. So, when I am speaking, I am creating a disturbance in the air out here, in that I am creating a pressure difference. That pressure difference travels, but the material particle does not go from one place to the other. Similarly, in water waves, I create a disturbance that travels from one place to the other, but water does not move from one place to the other. So, what we are talking about in a wave is, suppose I am thinking of a wave traveling towards the x axis. If I have a disturbance, and let us call it or denote it by disturbance x at time t equal to 0, it travels undistorted. What it means is that as it moves, it remains pretty much the same. So, let me try to make it pretty much the same as well as possible, except that it has moved by a distance v t. The function has remained the same. How do I describe this function as a function of x and t? Since the function has changed, only the position, it is nothing but f, the origin has shifted by v t. So, I can write this as f x minus v t time t equal to 0. This is f x minus v t, and this is f x at time t equal to 0. So, what we are saying is that the disturbance remains the same and it has shifted by a distance v t. So, this is what I will call description of a wave propagating with speed v along the positive x axis. In a similar manner, I can think of this wave propagating in the opposite direction, then it would have moved by a distance minus v t, and I would write this function which was x 0 going to f x t, which is f x plus v t 0. That is how the function changes as it moves along. There is another way of looking at it. Suppose I plot this function with respect to time. At x equal to 0, let us say this is at f x equal to 0, and it is given as a function f at x equal to 0 as a function of time t here. Then if I am looking at function at x at the same time, it would be f x t is equal to function at x equal to 0 at a previous time t minus x over v. That is another way of representing a wave traveling to the right. If the wave was traveling to the left, I would have had f x t equals f at x equal to 0 at time x over v. So, this is another way of representing a wave. What does this mean in terms of the equation? Let me now work with the form f x t is equal to f x minus v t for right traveling wave. The second term is 0, so I do not even write it, or f x plus v t for the left traveling wave. Let us differentiate for the right traveling wave this with respect to x, which will be df by du by dx, where u is equal to x minus v t. This gives me df by du itself. Similarly, df by dt is going to be df by du times du by dt, which is minus v df by du. This immediately makes it clear that for the right traveling wave, I have df by dx is equal to df by du, which is equal to minus 1 over v df by dt. And this is the wave equation for wave that is traveling to the right. For the wave which is traveling to the left, this sign will become plus. So, I have got an equation for the wave which is traveling to the right, which is df by dx is equal to minus 1 over v df dt, or for the wave which is traveling to the left, df by dx is equal to 1 over v df dt. In both, I can say that df dx in the upper one is equivalent to taking a derivative with respect to t and multiplying by 1 over v. In the second case, I can say that df dx is equivalent to, I should put an equivalent sign, plus 1 over v d by dt. These are valid wave equations for wave traveling to the left or traveling to the right. What about a wave which is a superposition of the two? What about a wave which does not travel? And do I have to always specify whether it is traveling to the left or traveling to the right? We do not do that. Instead, we combine these two equations, write a general equation for any wave which may be traveling to the left, traveling to the right, or could be stationary wave, not traveling at all, like a string vibrating. In that case, as you notice that since we wrote d by dx is equivalent to plus or minus 1 over v d by dt, this immediately implies that the second derivative d2 by dx square would be nothing but 1 over v square d by dt square. And therefore, I can write for any wave traveling to the left or traveling to the right that d2f by dx square is equal to 1 over v square d2f by dt square. This describes a wave traveling to the left, traveling to the right, or a superposition of the two, or a stationary wave, or whatever. If I can get for the motion of a disturbance in a system an equation like this, then I automatically get v also. Let us now see this through examples. As example 1, I take wave on a string. That is, there is a string which has tension T in it and its mass per unit length is equal to mu. If I distort it, assuming that the amplitude is very small, this amplitude is very small, then if I take a small portion in it right here, if I look at this portion moves up and down as the wave progresses, and let us get the equation for that. This moves up and down because there is a restoring force because of the tension. Now, let us look at this part here. There is tension T pulling it this way, there is tension T pulling it this way. This tension on the right hand side has two components, T cosine of, let us call it theta 2, and vertical component T sine of theta 2. This angle theta 2 is going to be slightly different from the angle on the left hand side. This is going to be T cosine of theta 1 and this component T sine of theta 1, and therefore, the net vertical force is T sine theta 2 minus T sine theta 1, and if the amplitude is very small, I can roughly write this as T theta 2 minus T theta 1, and the horizontal component is T minus T, which is 0. So, this disbalance in the two vertical components makes the string go up and down. Let us calculate theta 2 and theta 1. So, we are looking at this string and a small portion here. The net force is T theta 2 minus theta 1. If I take the length here to be delta x, theta 1 is roughly tangent theta 1, and if we take this displacement to be y as a function of x, this is partial derivative dy by dx. I am writing partial because y is a function of x and t both. Theta 2 on the other hand is going to be tangent theta 2, I should not write an approximate sign, this is exactly equal, which is equal to dy by dx at x plus delta x at the same time t, which I can write as equal to dy by dx at x and t plus the second derivative d2y by dx square delta x by tail expanding it. So, the vertical force comes out to be T, theta 2 is dy by dx at x t minus or plus d2y by dx square delta x minus dy by dx at x and t. This cancels and this is what I get. This force is equal to T d2y by dx square delta x, and this should be equal to the acceleration of this small piece here. Its mass is going to be mu times delta x d2y by dt square. That is the acceleration. You combine the two, delta x cancels from both sides and you get d2y by dx square is equal to mu over t d2y by dt square. This is precisely the wave equation we had obtained earlier, and therefore, there is going to be a wave setup in this string. It could be a progressive traveling wave, it could be a stationary wave, but this is the wave which will be going to be set up with the speed square v square being equal to t over mu. So, this is one example how wave equation is obtained in a system, and that automatically gives you the speed of wave also. As a second example, I will take pressure wave traveling down a tube in the direction x. For this, I consider a portion of gas or liquid in this, which is here, of length delta x. This is at some pressure P, and we create an extra pressure here delta P, so that the left hand side moves by a distance y x. This pressure propagates and it also changes its position, so that on the right hand side this line moves by y x plus delta x, and pressure out here changes by delta P plus some delta, let me call it 2 P, which is the second order. What we want to do is see this pressure difference, what force does it create, relate that to the acceleration of this small portion that we have taken, and see what is the equation that we get. First, what this delta P does is changes the volume. Let us first calculate the change in the volume. Assuming that this cross section out here is A. So, change in volume is going to be A y at x plus delta x minus A y x. This is a change in the volume of this portion that we took between two vertical lines, and this is nothing but A dy by dx delta x. This change in volume is caused by this pressure delta P on the left hand side, delta P plus delta 2 P on the right hand side. This delta 2 P is the unbalanced force that actually gives rise to the acceleration of this portion. So, the compression comes from this delta P. By definition, delta P is equal to dP dV times delta V, which I can write as V dP dV delta V over V. Notice that this quantity V dP dV is the bulk modulus, and therefore, I can write this as minus B, delta V is A dy by dx delta x over the volume of this element is A delta x. So, delta P is given as minus B, A cancels here, dy by dx. So, what we have calculated is that in this tube, which was at pressure P, when I apply a delta P here, the small volume here changes, and this delta P is given as minus B dy by dx. The pressure on the right hand side is delta P plus delta 2 P. So, delta P plus delta 2 P is going to be minus B dy by dx at x plus delta x, and this is going to be minus B dy by dx at x minus B d2y over dx square times delta x. So, unbalanced force is going to be this pressure here acts to the left, the delta P out here acts to the right, and therefore, unbalanced force is going to be B dy by dx x plus B d2y by dx square delta x minus B dy by dx at x. This is nothing but delta P, this is delta P plus delta 2 P. This term cancels, and I get the unbalanced force to be B d2y by dx square delta x, which is going to give an acceleration to this portion out here, and that acceleration is going to be d2 y by dt square, and the force should be equal to mass times this acceleration, and mass of this portion is going to be its volume A delta x times the density rho, and I should also apply for the force by area out here. Let us cancel things on two sides. I cancel this a, we cancel this delta x, and we end up getting the equation that b d2y over dx square is equal to rho d2y by dt square. And therefore, the equation is d2y by dx square is equal to rho over b d2y by dt square. This immediately gives me that velocity square is b over rho. You know this formula, that velocity of sound in a medium is square root of b over rho. When we wrote b, which was equal to minus v dp by dv, we did not specify whether it was at constant temperature or adiabatic. You know very well that what is argued is that when the changes are taking place in air, hardly any heat transfer, therefore, we take bulk to be b at q equal to 0 or adiabatic b. So, let me write this adiabatic b. So, I have shown you two examples where by considering the equation of motion, we got an equation which is the wave equation from which we could determine what the speed of sound or speed of that disturbance or speed of wave in that medium is going to be, and finally, this wave equation actually its solution gives me how this disturbance is going to travel. Now, a particular example of this is the plane wave, whereby it depends only on x and the amplitude is all over, it is independent of y and z. So, for example, if I have x, y and z, a plane wave would have this wave front which has the same amplitude all over the y z plane, and this disturbance travels in the x direction. We also consider harmonic waves which have a disturbance y x t is equal to a sine 2 pi x over lambda minus nu t. You can see this satisfies the equation d2y over dx square in this case is going to be minus a 4 pi square over lambda square sine of 2 pi x over lambda minus nu t, and d2y over dt square is going to be minus a times 4 pi square nu square sine of 2 pi x over lambda minus v t, and you can check that this then satisfies the wave equation with velocity being equal to nu times